Okay. All right, we'll go ahead and get started. So thank you for coming today, especially in light of our COVID precautions that we're taking, and our museum here is doing an excellent job on keeping everybody safe. And so I appreciate you all still coming out today, being able to see this. So we'll have a good time today. So my name is Guy Hanson, and I'm a scientist from Eli Lilly and Company, where we make medicines, hopefully life-saving medicines. And as we make medicines, we use a lot of different types of science. But probably the main area of science that we use is chemistry. Chemistry. And chemistry, of course, is the study of chemicals and how they behave. But more importantly, what happens when you mix chemicals? What can you make? So we make medicines. But you can also make a number of different things, like plastics, like this face shield I'm wearing, or you can make fuels like gasoline or food or clothing, cell phones, tennis shoes, all different things using chemistry. And that's what we're going to look at today. But the most important thing about chemistry, actually more than any other area of science, is safety. Safety is very, very important. So what's one thing that I'm wearing that has to do with safety? Anyone? Yes. Yeah, my glasses protect my eyes, yeah. Yes. Face shield, and that's to protect you and me, I guess, from our COVID. And what else am I wearing? It has to do with safety. Anything else? Yes. Yeah, my lab coat. My lab coat. And this lab coat is very important. This lab coat can save my life. Because if I spill chemicals on my clothes, my wife will kill me. Okay? Very, very important. So safety is very, very important. So all of these experiments have been tested to make sure they're safe and to make sure they work. Wouldn't be a very cool show if they didn't work. So let's get started. So we know that things exist in one of three ways. They're either a solid, a liquid, or a what? Gas, right. The three states of matter: solids, liquids, and gases. And we're going to look at all three today. So let's start with a liquid. How many have ever seen a jar like this? Yeah, it's a canning jar or a mason jar or a ball jar, all the same thing. It's made out of glass. A lot of times it's used to can vegetables like green beans or tomatoes, or to put jelly in. So this glass jar, it's got a lid that tightens down. And then inside that lid is another lid, which I've taken out. And you can see I've got water in here, ordinary water. And this lid just fits on nice and loose. In fact, I can set it on there and just knock it right off. It's just a very loose lid. So I'll set the lid on there, kind of press down on it a little bit, hold it over this bucket upside down. Now what happens when I let go of the lid? Yeah, that water is going to come gushing out. It does not come out. And actually, all of you know why. Can somebody tell me why that water does not come out? Yes. Because it's too tight. Yeah, maybe I put that lid on there real tight. That's a great guess. But that lid is actually very loose. There's another reason. Yes. Air. Very good. Actually, it has to do with this airspace, which this airspace creates what's called a vacuum. And we all know what a vacuum is, because we've seen vacuum cleaners pick up dirt and pick up dust, and that's what this airspace is doing. It's acting like a vacuum cleaner, and it's trying to pick up the water. And while it does, it holds the lid on. But what happens when I slide that lid out? Yeah, that water is going to come gushing out, isn't it? Now, as scientists, when we do experiments, we like to repeat them at least once to make sure we've learned everything we wanted to learn from it. So here's our jar, here's our water, here's our little air space, here's our tight lid, here's our loose lid. Okay, nice and loose. I set it on there, hold it over the bucket again. Now we know what happens when I let go of the lid. Yeah, the water stays in, and we know why. Why does it stay in? Vacuum. Wow, very good. And what happens when I slide the lid out? The water goes everywhere. What? It did not go everywhere. what is going on here? Now, normally, on non-COVID times, I like to walk up and down the aisle so you can see what's up underneath here. And what you would see is another lid. But it's not a lid like metal, like this. It's not a lid like a plastic coating. What it is actually is a screen. The same kind of screen we put in our doors and windows. And the screen is holding in the water. Oh, well, that makes sense. Well, wait a minute, does that make sense? I don't know, because if I had a big screen between you and me, and I took a bucket of cold water, and I threw it through the screen, you would get soaking wet. So why doesn't the water come out of this screen? It's an ordinary screen. Oh, I heard somebody say it. Surface tension, very good. Very good. You think, what does he mean by surface tension? Well, you know the holes in a screen, are they big or are they small? They're small. And each one of those holes gets filled with a drop of water, and it forms a little wall of water. We actually call that a thin film. And that thin film of water is holding in the rest of the water. It spreads out the surface. That's what he's talking about, the surface tension. But you know, if I let a little air in this just by tilting it, and the water comes out. But once I straighten it up, it fills those holes and holds the water. So that's kind of cool. The only difference between these two jars is one has a screen and one doesn't. So you might think, okay, well, that's kind of cool. But you know, as scientists, when we do experiments, we like for them to tell us something. We like to learn from them so we can do more experiments. And so what do we learn from this? This experiment tells us why we do experiments. Because you know, if somebody just described this to me, if they said, hey guy, I've got a jar with a screen and some water, and I'm going to pour it out, I would think it'll just pour right out. So we don't know the answer until we do the experiment. That's why as scientists, we love to do experiments. That's how we find out how things work. All right, let's look at some gases. So these balloons are filled with different gases. And do you think the gases in these balloons are heavier or lighter than air? Lighter, that's right. That's why I had to tie them down. Can somebody give me the name of a gas? Yes. Helium, very good. How about another gas? Yes. Air. And air contains mainly two things. Another one, yes. Hydrogen, good. Another gas? Yes. Oxygen, that's one of the things in air. Very good. What do we breathe out all the time? Carbon dioxide. Very good, carbon dioxide. And also we breathe in oxygen, we breathe in nitrogen. So there's a lot of different types of gases. And we can go on and name gas after gas after gas. But the hard thing about gases is they're very difficult to tell apart. If I have a handful of carbon dioxide and a handful of oxygen, I can't tell them apart. I can't see them. I can't feel them. I can't hear them. I can't smell them. I can't taste them. I wouldn't want to. I can't tell those gases apart. So one way that we use to tell gases apart is a flame test. A flame test. Oh, yeah. And that's what we're going to do with these balloons. We're going to try to determine what gases are in these balloons by doing a flame test, okay? So, I have on the end of this pole a candle, and I'll light the candle and touch the balloon, and we'll see what kind of gases we have. Well, let's check this first, this pink balloon out. All right, so we get a little pop, a little louder than air. Let's check this blue balloon out. Whoa. So, yeah. Now we're getting somewhere. So you notice two very different results because two very different gases. The first balloon contained helium. Helium. And helium's the gas they use in blimps. They used to call them dirigibles. They use in blimps so that the blimp, goes up in the air. Now, years ago, they used to use this gas, the gas that gave us the fire in blimps. And you can see why they don't use that in blimps anymore. Just one little match, and that whole blimp would go up. Does anybody know what the name of this gas was that gave us the fireball? I heard somebody say it. Hydrogen. Yeah, very good. Hydrogen. So we saw helium, we saw hydrogen. Very different. So let's do some more balloons, but let's get you involved in this. I wish I could have you come up, but I can't because we want to stay safe, so distance-wise. So raise your hand and tell me which color balloon to do next. You can pick any balloon, but not the red one. Okay, yes. Yellow? Okay, yellow it is. Let's see what we get. All right. So what gas was that? Helium. Very good. Yeah. Which color? Purple. Whoa. What gas was that? Hydrogen. Okay. Another color. Yeah. Green one? This one? Okay. All right. Another helium. Okay, which color next? Orange. You want the orange? You got it. All right. So, you can pick any balloon you want, but not the red one. Which one do you want? Good choice. Green, okay. All right. So, that leaves us with the red balloon. The only red balloon up here. The one we've been saving for last. How many think this balloon is filled with helium with a pop? How many think it's filled with hydrogen with a fireball? How many think this balloon, the only red balloon up here, is filled with whipped cream? Ah, well, you guys are going to find out. Okay, here we go. Very good. So hydrogen. So, you see that different gases, they behave differently. They have different properties. So they behave differently. Some of them give us a pop, louder than air. They're called combustible. Some of them give us a fireball. They're called flammable. So the two gases that we breathe in mostly, oxygen and nitrogen, are very similar to helium and hydrogen because nitrogen is not flammable. It's combustible. Oxygen is flammable. In fact, if all we breathed in was oxygen, and this room was filled with oxygen, and it's all we were breathing in, and I were to light this candle, or this match, the air itself would catch on fire. That's why we're glad we don't just breathe oxygen. But if it was filled with nitrogen, I would go to light this, it wouldn't even light, because it needs oxygen to burn. Also, we need oxygen to live. So that's why we're glad it's just the right amount of oxygen and nitrogen here on Earth. The only place, the only planet that has just the right amount of oxygen and nitrogen for us to live on. That's why we live here. Very good. All right, another thing. Did anybody notice something kind of unusual, that after I would light some balloons, I would do something with this stick, but not for every one? Did anybody notice anything unusual? I had to relight the candle each time, but then there was something else unique, something different on some of the balloons I had to do with this stick. I always had to relight it, but yes? Well, I did have to poke it, but did you notice that sometimes, boom, it would just go out, like on helium. And that would be it. Then on hydrogen, did you notice the candle stayed lit and I had to kind of put it under my face shield and blow it out? And the reason is, remember, helium is not flammable. So it would blow the candle out, just like if we blew the candle out. Whoops. But hydrogen is flammable. So when I would light it, it just loves that flame and it would not put the flame out. Okay, so that's what I mean. That's an ideal way on a flame test. A flame test. All right, let's do another experiment.
What kind of experiment?
Well, I'll show you. Let's see. Let's do this one. So, can somebody tell me? Can you tell me what that is? What's it look like? A coin, yeah, it's a penny. Very good. It's a penny. And so what I have here is a penny, and I've got a hollow pipe. Now, can somebody tell me what metal are pennies mostly made out of? Yes. Copper, right, copper. So what I'm going to do is I'm going to take this penny, and I'm going to drop it into this hollow pipe right over this empty bucket. And when I do, how many think this penny is going to land in that bucket? How many think this penny is going to go up in the air? Okay, let's find out. So here's the bucket. Here's the penny. Okay, so that wasn't very exciting. It landed right in the bucket. And we all know why, but only using one word. Can you tell me why that landed in the bucket? One word only. Gravity. Very good. So now, I've got this steel ball, much heavier than the penny. And we're going to do the same experiment with this hollow pipe. I'm going to hold it over this bucket and drop this steel ball into this pipe. And when I do, how many think the steel ball is going to land in the bucket? How many think the steel ball is going to go up in the air? How many don't know? And that's a good answer in science. How many want to find out? That's the best answer in science. All right, here's the steel ball. Here's the pipe. What? Let's do that again. Hollow pipe. Here's the steel ball. We drop it in. Where's it at? So, only using one word, can you tell me why this steel ball wanted to stay in this pipe?
Because
one word.
To be alone.
What is it? Magnet. Very good. It's a very powerful magnet. What was your answer? Very good. Okay, a magnet. Very good. This is a very powerful magnet. And magnets give off a force field. And that force field is pressing against the inside of the pipe. So when I drop it in, it stays and stays and stays, and then gravity pulls it out. So two forces working against each other, gravity and magnetism. Now let's take this same experiment with the magnet, and let's look at this pipe. So let's put it in there just like we did before. Stays and stays. And then, let's look at this little fellow, okay? We take this pipe, same magnet, and then it drops out. And somebody tell me, what do you notice different about these three pipes? Anything different? Yes. Different lengths. Very good. What else? What else? Yes. Different materials. Very good. So this is copper. This is zinc. If you take these two metals and you melt them down together, you get this, which is brass. Copper, zinc, and brass. Now, they're different lengths because they are different materials. Because that magnet, if you had a timer and timed it, which we did, it stays in each of these pipes the exact same amount of time. Now, for us to be able to do that, we had to adjust the length of these materials because each of these metals, even though it's the same magnet, they all act differently. They have different properties. Just like we saw with our gases, they act differently. So many times in science, that is a key concept for us as we study not just nature, but as we study chemical principles, that things act differently. And how can we use those different actions, work those together to make things? Like medicines, like cars, like all cell phones, all different things that we use. All right, let's do this one.
That one.
Oh, this one, you'll like this one. So can somebody tell me the chemical formula for water?
Water.
Chemical Very good. H2O, 2 hydrogens and 1 oxygen tied together or bonded together to give us water, which is normally a clear liquid, and it looks just like this. But this is not water. This is hydrogen peroxide. And hydrogen peroxide looks just like water, but acts very different. And a lot of times we use hydrogen peroxide in our homes for cuts. If you get a cut on your hand or on your finger, you put some hydrogen peroxide on it, it kills the germs in that cut. So wait a minute, if hydrogen peroxide is used for cuts and we put it on our hands, why in the world am I wearing these very special gloves to protect my hands? Yes. Because it would sting, is that what you said? Very good, that's exactly right. He said because it would sting. And that's right, if I took this glove off and I poured this on my hand with no glove, it would feel just like I went over and put my hand right in a fire. It would burn that badly. So this is a pretty nasty chemical, pretty dangerous. And you know, it wouldn't be safe just to leave it sitting around the museum. So I think what we're gonna do, let's take that liquid and let's just tear it in half. Just like you would take a paper towel and tear it in half, let's just tear that liquid in half. So you might think, well, wait a minute, how can we tear a liquid in half? Well, to help us see this, let's add a little bit of dishwashing soap. And we'll mix that all up. And let's add a little bit of food coloring. How many want red? How many want green? How many want blue? I don't have blue. How many want red? How many want green?
Green.
Wow, red. Green. Wow, we'll go red. That's pretty even. Okay. So now we have a red soapy hydrogen peroxide solution. Now remember, what we want to do is we want to tear this liquid apart. And you know, when you tear chemicals apart, or when they fall apart on their own, it's called decomposition. Decomposition. And this would fall apart on its own if we let it sit here for 90 days. So we'll wait. No, we don't want to wait 90 days. And you know, in our labs, we don't want to wait 90 days for this reaction and 2 weeks for that reaction and a year for that reaction. So we use chemistry to make our chemical reactions go faster. And that's what we're going to do here. We're going to use a type of chemical known as a catalyst. A catalyst. And all a catalyst does is take a chemical reaction and make it go very fast. In fact, when I add this catalyst to this hydrogen peroxide, this 90-day reaction is going to happen in 2 seconds. 1, 2. Let's see how it works. Now, what I need from you is a 5, 4, 3, 2, 1 countdown. Ready? 5, 4, 3, 2, 1. Wow. So, somebody tell me, what did you see?
Cotton candy.
Looks like cotton candy. What'd you see? Explosion. Very good, yeah. In fact, came out very fast. In fact, if I had taken this catalyst and I had dumped it in like I did, but I pressed down on this very, very hard, and I would have just held down on this, this would have built up pressure, and this whole thing would have exploded, okay? Now let me ask you this. How many think this is, if I touch it, this is hot? How many think this is cold? How many think it's not hot or it's not cold, it's just room temperature? All three are good guesses. This is actually very, very hot. And the reason is when you tear chemicals apart, they don't like that. So they give off energy, many times in the form of heat. It's no longer hydrogen peroxide. We tore that apart. It's now just water and food coloring and soap. But the water in there, you notice I'm not touching it. The water in there is so hot, it's actually boiling. It's actually boiling. Now, we like to give our experiments very scientific names. So we call this experiment elephant toothpaste. Very good. All right, should we do another experiment? Okay, let's do another one.
Which one are we going to do?
Well, I think we'll do this one. So what I have here is water. And this experiment, this is where COVID is difficult because this experiment, I'd love to do this with a student volunteer, but we can't today, so I'm going to have to be the presenter and the volunteer. So I volunteer, but this is water, and I'll see if it's kind of cold. I've got some cold water here. So let's see what kind of crowd we have here today. How many of you would like me to take this cold water and dump this on my head? What? I mean, I got a lab coat on, I guess, so my clothes would be dry, my hair would be drenched, water dripping off of my face mask and all that, but you guys did vote, so I guess we have to do it. Now, you know, it wouldn't be a chemistry show if we didn't mix chemicals, and of course, water's a chemical, probably the one we're most familiar with. And then I have here a little bit of a powder. Uh-oh, you remember what happened the last time I used a little powder? We made elephant toothpaste. But this is not a catalyst, it's something different. And I'm going to take this powder, dump it into this cold water, count to 5, and then I'm going to dump this on my head. All right, here we go. I can't believe you guys are having me do this. Here's the water. Here's the powder. 1, 2, 3, 4, 5. What? What in the world happened?
It was sticky.
Yeah, it looks like it went sticky. We started with water, a liquid, and now we have this solid. And what we have made here is something that all of you have used. And this is being used in most of your homes right now. What is this?
Sticky.
Sticky, that's a good guess. Not sticky. Ice, that's a great guess. It's not ice. Right there. Slime, it's not slime. Yes. What is it? Glue, like Elmer's glue. That's a great guess. It's not glue. Thought I saw another hand. Yes. Jell-O is a real good guess. It's not Jell-O. Yes.
A solid.
A solid. You got that right. It is a solid. I'll give you a hint. Does anybody know what a candle is made out of?
Wax.
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 It's not wax. Okay, what is this? Yes. Going to consult with Mom there. Okay, think about it. There's one right up the top. Soap, that's a good guess. Yes. Hand sanitizer, that's a good guess. This actually is how they make disposable baby diapers. What? You guys just about had me pour a baby diaper on my head? And the reason is that little bit of powder absorbs or locks up 100 times its weight in liquid. It's called superabsorber. Now, chemical reactions, if they work, they go forward like elephant toothpaste. But you know, I can't make this go backwards. I can't grab all that foam, push it down in there, and turn it back into hydrogen peroxide. But some chemical reactions, they go forward and they go backwards. And we can make this go backwards just by adding ordinary table salt, just like what you would get out of a salt shaker. Does anybody know the chemical name, 2 words, for salt out of a salt shaker? Yes. Sodium's the first word. Chloride, sodium chloride, very good. So we'll put some sodium chloride in here, table salt, and we'll mix this all up. Of course, when you add salt to water, you get salt water, which is very cloudy. And as we mix it up, now our solid goes right back to a liquid. So how many think I should take this and pour this on top of my head? What? No, we won't do that. But what does this mean? Remember, we like to do cool science, but we like for it to mean something so we can do more science. Well, what this means is if you live down in Florida, let's say, right by the ocean, and tomorrow you went to the beach, that'd be a great day, and you're there at the beach, and your little baby brother or sister is sitting on the beach in their diaper, and the salt water comes up and hits their diaper, that diaper's just going to fall apart. Yeah. But we live in Indiana, so we mainly swim in pools. So you go to a pool next summer, and your little baby brother or sister's in their diaper, sitting in the kiddie pool. Well, unless they have a very special type of diaper, their diaper is going to get bigger and bigger and bigger because it's trying to absorb all the water in the pool. Super absorber. Very good.
Like this big?
Yeah, like huge. Okay, let's do another one.
Which one?
So, you know, summer's gone and we're in fall, coming into winter. And what's one thing that we usually have around winter, especially around Christmas time? What's one thing that we usually have falling on the ground? What is it? Snow, that's right. Well, it's a little early for snow, but you know what? I think what we're going to do is we're going to go ahead and make our own snow. We're going to make our own snow. So you might think, oh, well, you're going to need a refrigerator or a freezer. Well, not at all. We're just going to make our snow right here. And this is our snow. Right there, there's our snow. And so you might say, wait a minute, that doesn't look like snow. In fact, it kind of looks like sugar or salt. And it feels like sugar or salt. But that's our snow. You think, how can that be? Well, let me ask you this. What's the main ingredient in snow? Water. Yeah, water. So I just so happen to have some water here. So let's add this water to this snow powder, and let's see what we get. So I'm going to add all of this water, because we know that snow has a lot of water in it. And so I want this to have as much water as I can get into this powder. Okay, all of the water. Now comes, again, the part I'd love to have a student do, but I have to do it. And that is where we go in and mix this up. Now, this is usually where you would see a student going like this, because what they feel starts off a little slimy. Now it's getting cold and colder and colder and colder. And the slimy is kind of turning into powdery and fluffy and super soft, because what we're making here is, get that off my hands, artificial snow. And this is how they make artificial snow. So if somebody wants to go sledding or they want to go skiing and there's no snow on the hills or slopes, You take that powder and some water and a big fan, and you blow that out over the slopes, and you get artificial snow. Now this snow is super soft. It's softer than any pillow that we have. It is like super soft. The other thing is, you notice that we have 1 gallon of water, so that's 4 liters. And we added that just to that little bit of powder, and we are now at about 6 liters. So how did we grow from 4 liters to 6 liters? And the way we did that is that we made volume. You know, there's certain things you can't make, like it's called conservation of energy. So you can't just make energy, it has to come from somewhere. Same way with matter, it has to come from somewhere. But volume, you can. And we grew our own volume right here. Now this artificial snow, very fluffy, very soft, and I think we've all slipped and fallen on the snow or the ice, and it hurts. If you fell on this, it would be like falling on the softest blanket stacked up about 12 deep. It's just super, super soft. So you might think, well, wait a minute, if they put this on snow slopes, how do they get rid of it? How come is it still there? Because this snow, if you came back tomorrow at this time, it would look just like this. If you came back a month from now, it would look just like this. If you came back a year from now, it would look just like this. So it's like, wait a minute, how do they get rid of it? The way they get rid of it is dissolve it in water. Oh, wait a minute, yeah, how does that make sense? Because we added water to it. But to dissolve this much snow in this bucket, you would have to use 5 of these filled with water. It'd take that much water, but it would dissolve. And that's how they get it off the slopes from rain. Now, an interesting thing. You know, when we did this experiment with the diaper, and we do this experiment making the snow, and I added the powder for the snow, and I added the powder for the diaper. These are the exact same chemical. Wait a minute, we didn't get the same result because this overflow, I mean, it looked like it was going to overflow. This kind of stayed in the jar. They're the exact same chemical. The difference is the way they're shaped. It's called crystal form. If you looked at these under a microscope, you would see a crystal like a snowflake. But this snowflake would look different than this snowflake. And because they're different, they behave. They have different properties. And we've been looking at different properties of chemicals with our gases, with our metals, with our liquids. So we're used to that. We're accustomed to that. All right. Another experiment? Yeah. Okay. You guys are excellent. Let's do this one. Now for this experiment, I'm going to need to get something extra here. Okay. And can you, this young lady here, can you tell me what that is? Yeah, it's a $20 bill. And what's your first name? Adrian? Avery, is that right? Avery. So, this is a $20 bill, a normal $20 bill. If this experiment does not work, then Avery gets to keep this $20 bill. That'd be okay with you, wouldn't it? Yeah, okay. So you know, a lot of times you get some money, you know, you earn some money or you get some money as a gift, and you say, I've got $20, I know just what I want to spend it on. I know exactly what I'm going to buy. Well, people will say, you've got a little money, and it's burning a hole in your pocket. Well, what in the world are they talking about? Well, all that means is you're very anxious to spend it. Well, you know, as scientists, we like to test things out. So we're going to test out this idea of having some money and it burning a hole in your pocket. We're going to take this 20 that Avery would like to have, right? Yeah. And we're going to test that idea out. But we're going to make it a little more difficult. We're going to take this 20 and we're going to get it soaking wet. Okay, so it is soaking wet, and now we're going to test out that idea of burning a hole in your pocket. So there's our 20. Oh wow, there it goes. Wow, look at this. It didn't burn up. And in fact, if you could touch this, you would feel it is cold. It's very cold. Can somebody tell me, why didn't this burn up?
Because it never burns.
It didn't burn, right? Wet with what? Water. Yeah, it's covered in water. That makes sense. But you know, if I go over to a swimming pool that's filled with water and I light a match and I throw it in that pool, the water doesn't catch on fire. Why does this catch on fire? Yes. Oh, very good. He said because it's alcohol. So you're saying this is not just water. Very good. That's right. This is a chemistry show. And we like to mix chemicals on this show. So this has water in it. Yeah. And rubbing alcohol. And the rubbing alcohol catches on fire and the water puts it out. But it has to be just the right amount of water and just the right amount of rubbing alcohol. What if I had too much water in here? What would happen to this? Yes. It wouldn't even catch on fire, right? What if I had too much alcohol? What would happen? Yes. It would just burn up. That's right. Has to be just the right amount of each. Now the good news for Avery, for coming to the Children's Museum today on a Saturday and for letting me do this experiment and recognizing this is a $20 bill, Avery lets me keep this $20 bill because the experiment worked. Let's hear for Avery. Good job, Avery. So you see, it has to be just the right mix, otherwise it doesn't work. All right, we have one more experiment. So I have a very, very tough question for you. So you want to think about it before you answer. Think carefully. How many here have ever ridden in a car? Oh yeah, all of us have, haven't we? Well, what makes that car go? Gasoline. Where's the gasoline go? Engine. Yeah, the gas tank, then to the engine. Well, you know, inside that engine, there are chemical reactions. There are actually explosions. They're called combustion. And I would love to have a car here and take the engine apart and show you how that works. That's kind of big to carry. So we're going to make our own engine. This is our engine right here. Okay? Now what we're going to do is this is going to be our engine and we're going to have combustion in here. But to have combustion or explosions or fire, to have a fire, you have to have three things. You have to have three things. This is very important to firefighters. They need to know those three things. What's one of the things you need for a fire? Yes. Oxygen, yeah. What's another thing you need? Yes. A lighter, right, a light source. There's one more thing you need for a fire. Yes. Air, that's where you get the oxygen. There's one other thing. Yes. What is it? Fuel, gasoline, yeah. So, we know we have oxygen, right? And now we're going to need some fuel. And what we're going to use for our fuel is methanol. This looks like gasoline, a liquid, but it's methanol. And methanol is used actually in Indy race cars. But I'm going to put a little fuel in here. I'll put a little, maybe a little more. More? A little more? 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 Did I hear somebody say the whole thing? Wow, you guys really want an explosion. Okay. So now we've got all of our methanol in there. I'll put a little stopper on top. Now the interesting thing about fuel is many times with these liquid fuels like gasoline or methanol, you don't necessarily have to have the fuel to have combustion. All you need are the vapors or the gas from the liquid. So I'm mixing this up, letting those vapors come in there, and we don't really even need the liquid. I can pour all the liquid right back into the jar. And trap those vapors, and now we have those vapors. And remember, we have oxygen, we have our fuel, now we need our light, our flame source, which we know we have. And what I'm going to do is I'm going to light this candle. I'm going to take the stopper off and hold it over that, and keep your eyes on this engine right here, and let's see what happens. So, somebody tell me, what did you see?
It was a big fire.
A big fire. What color was that fire?
Blue.
Blue. Very good. And that blue fire tells us that it's methanol. Okay? If it had been gasoline, it would have been red. Okay? So again, different chemicals, they give us different results. So we saw blue flame come out of there. And it came out very strong. And if you kept watching it, it came out of there, and then the flame went back down. You could hear this whoosh. It went back down to chew up the rest of the methanol. Now remember, we poured all of our liquid off. We didn't have our liquid in there, but if you look in the bottom of this, we have liquid down in the bottom of this. What is that liquid? Water. Very good. Water, that's right. Because chemical reactions, they usually make something. Like with our balloons, we made fire. Here we made foam. Here we made snow. Here, this chemical reaction makes water. Different chemical reactions, they make different products. Wow, very good. All right, you have been excellent today, and that's our show. Thank you. Very good. All right, enjoy your time at the museum. Thank you so much for coming out, and be safe.